What do you think this is? It's an unusual view of a human spine, which brings us to another way in which the bones in our bodies serve us by protecting important organs. The vertebrae, these separate sections of the spine, form a sort of tunnel, and it's inside this tunnel that the spinal cord passes down from the base of the brain, carrying nerve fibres which branch off to every part of the body. You can see it exposed in this model. Parts of the vertebrae have been cut away. Normally, the cord is well protected as it passes down inside them. But if we misuse our spines, nerves can still be damaged, especially at the base of the spine and here at the neck. These yellow projections on the model represent nerves. They can be trapped, pinched if you like, if damage occurs to the discs between the vertebrae. If you pick up a heavy weight the wrong way, a disc can be damaged. You mustn't bend your back like this. If you do, when you start to lift, the discs get more compressed at one side than the other, like this. You'll remember that they're hollow and contain a fluid. This sort of uneven pressure can cause a disc to burst, so that this happens. The damaged portion can trap a nerve against the bone, causing the intense pain of what's called a slipped disc. It's the discs down here, in what's called the lumbar region in the lower back, that are particularly likely to cause trouble, trapping nerves such as this one if they rupture. Any of these discs can be damaged if we don't control our spines properly and take great care when lifting or moving heavy objects. This is how you should do it. Bend the legs and not your back, and keep the spine as straight as possible while lifting. If you do this, then there's an even pressure on the discs, and they're not nearly so likely to be damaged. They can flex evenly, like this. Always take care to keep the spine as straight and upright as you can when you're lifting something. Try to let your legs do the work. Another wrong way to do something. Pushing like this could also damage a disc. Do it like this, keeping the back straight. It's also easier this way. An X-ray picture of the spine. And can you see another, smaller spine here? This is a pregnant woman, and her baby's nearly ready to be born. There's the baby's skull, and her womb has the pelvic girdle around it, another part of the skeleton which protects important organs as well as acting as a support. Here it is. This one's a male skeleton, and you can see how the pelvic bones form a sort of protective cage. The ribs form another protective cage in the chest. As you can see on this model, they enclose and protect the lungs, as well as the heart and other vital organs. That's the liver at the bottom. It's possible to see these living organs inside the body lying in the rib cage. This is an X-ray body scanner, which beams X-rays through the body from different angles. A computer is programmed to construct pictures of different cross-sections of the body from the amount of X radiation detected passing through at the different angles. There's the spine seen in an ordinary X-ray. The ribs, and the pelvis. Now let's look at a cross-section of the body at the level of this dotted line, through the upper abdomen. Here it is. This is the outside of the body. Here are portions of the ribs. The spine seen in cross-section, and the liver and other organs lying inside the rib cage. The skull protects perhaps the most important organ of all, the brain. Our brains are our control centres, the organs which make us the most intelligent of all the animals. The brain must be well protected against damage. The human brain is a highly complex organ, dispatching and receiving electrical impulses along our nerves, enabling us to act and to feel and to think. This picture, produced by nuclear magnetic resonance, using radio waves, not X-rays, shows the brain inside the skull case. In fact, there's a fluid surrounding the brain inside the skull, which acts as a very efficient shock absorber. Suppose this jar is the skull and an egg the brain inside. It's not all that well protected. But with a liquid of a suitable density inside, like the brain in its fluid inside the skull, it's much better protected. You can't break the egg. Of course, you could break the jar, and you can break your skull. That's why she's wearing a protective riding hat, and not just when jumping, but whenever she's riding. The same for motorcyclists. And for anyone working where there's a danger of a knock on the head. The skull won't protect us against everything. When you look at a prepared skeleton, such as this one, the bones look dead, because they are dead, and it's hard to believe that our bones are actually living organs, but they are. And as we'll see, pictures such as this prove it. This isn't an X-ray picture of the spine, ribs and shoulders. It's made by radiation coming from the blood supply within the bones. It's obtained like this. A syringe is filled with a solution of a weakly radioactive isotope. Its radioactivity will only last for an hour or two. The solution can be injected into the bloodstream when doctors want to know about a patient's blood circulation, for instance, and it can reveal other problems inside the body as well. As the isotope circulates in the bloodstream, the weak radiation it gives off can be detected using a special sort of camera. Here, the camera is detecting the radiation given off when the blood containing the radioisotope reaches the brain. A picture can be put up on the screen showing the radiation coming off from inside the head. The white areas show where the blood containing the radioisotope has got to. This technique enables us to see how the blood circulates, not only in the brain, but in other parts of the body as well. Here are the lungs, photographing themselves with the radiation from the isotope in the blood running through their blood vessels. But here's the point about bones. You can see the spine, ribs and pelvis, and the picture shows that there must therefore be blood circulating inside the bones for them to show up as these white areas. Another picture. The bones obviously have a blood supply. And that's because they're living organs, needing blood to feed them, to bring them fuel and oxygen, in fact, to keep them alive. The human hand. The bones inside it, like all bones, are alive. Look at the bones in the thumb, for example. On this specimen, you can see some of the small blood vessels which carry blood to the interior of the bone. They pass through tiny holes in the bone. Inside the bones, there's bone marrow, which actually manufactures important constituents of the blood, which pass into the blood as it goes through. And there has to be a good blood supply to bring to all the living cells the materials they need and carry away waste products. Bones have a definite structure. This is a dead rib. It's hard and springy. Here's another rib which has been decalcified. All the hard calcium compounds have been dissolved away, but there's still fibrous tissue left. It's so flexible you can tie a knot in it. This is the fibrous tissue in which calcium compounds are laid down when the bone is formed. And bones have a much more complicated structure than you might think. Look at the head of this femur, the thigh bone. There's a system of strengthening struts inside it. And look inside this section of bone. In the living bone, the tissues which manufacture components for the blood lie between these thin, lacy columns. So you see, bones are much more complex living organs than they might appear. When a baby is developing inside the womb, hard deposits of calcium compounds are laid down in the fibrous framework of the bones as the bones grow. The dark areas are where calcium has been deposited in this way. You can see that the process isn't yet complete. The bones are not fully developed. But bones of the skull, important protection for the developing brain, are quite well developed. Broken bones in the leg. Because bones are living organs, they can repair themselves after they've been fractured, even as badly as this. Sometime later, they've grown together again, but this can only happen if the broken bones are carefully lined up with each other, then immobilized. The correct first aid is very important. If she thinks she's broken her wrist, she must avoid putting any pressure on it and support it as well as she can until she can get help. A more serious injury, a suspected broken leg. The limbs must be kept as still as possible. You can improvise some sort of splint, say like this, using whatever's handy until expert help arrives. In hospital, wetted plaster of Paris bandages are wrapped around the broken limb. When they're dry, the plaster will support the bones inside her leg, keeping them still while healing takes place. Plastic splints can also be used. It's a skilled business. Actually, this lady is having a second plaster applied. She's had one from when she had the accident, and the surgeon manipulated the broken bones into the right position until healing was well underway. Now she's having another one. In a few weeks' time, this plaster will be taken off and she'll soon be able to use her leg again. The bones of the unborn baby. These are the bones which, when they're fully formed and ready, with their ligaments and tendons and muscles, enable us to stand upright, to walk and to run, while they protect some of our most important organs. Our skeletons are a fascinating and vital part of our living bodies.